Hello everybody, this lesson is going to be an introduction to the types of bonds that can get made and why those are the types of bonds that get made. So first, let's ask ourselves, why are we even going to bother making bonds? Why do atoms make bonds in the first place? So remember that the atoms want to have a full outer valence shell. They want to feel really stable, like the noble gases are. So what ends up happening is that the atoms are going to try to adjust the number of electrons they have until they look like a noble gas in terms of their configurations. So for example, neon and argon, if you look, their valence shell here, 2s2, 2p6, that's 8 electrons, that's nice and full. For argon, the valence level is 3, right? 3s2, 3p6, that ends up to being 8 as well. Now compare that to something like sodium. The valence energy level over here is 3, and it only has 1 electron there. That's not even close to 8, is it? If this sodium wants to look like a noble gas, it's going to have to change something because right now it doesn't look like one, does it? It does not have 8 valence electrons. It only has 1. So what ends up happening is a chemical reaction takes place, and that allows the atom to change the number of electrons that it has. It's either going to transfer electrons or it's going to share electrons. And that transferring or the sharing is what we call a bond. Okay, that's what connects it to another atom. And in that process, it ends up feeling more stable. And so it has a better valence shell. It has a full valence shell and is more stabilized. So that's the reason why the electrons want to be changed. That's why we get our chemical reaction. It's really important to understand that when we're bonding, only the valence electrons are participating. And that's because they're the ones in that highest outside energy level. They're the ones on the outside. And so if two atoms are going to bond, only the electrons on the outside are the ones available to be shared. The joke is that atoms are shallow. They only care about what's on the outside. So it's not like one atom can reach inside to the inside of another, right? It has to only interact with the valence electrons on the outside shell. So it's really important that you remember how to count your valence electrons. Remember, everything in column 1A has 1 valence electron. Anything in column 2A has 2 valence electrons. Column 3A has 3. 4A has 4. 5A has 5. 6A has 6. 7A has 7. And 8A has 8. Remember, we skip the D block and we skip the F block because they don't behave normally. So during a chemical reaction, you can kind of have several different ways of adjusting the electrons. In an ionic bond, the electrons are going to be transferred from one atom to the other. One atom's going to let go of the electrons, give them away, and one is going to take the electrons. One atom makes a cation, one makes an anion. One has a plus charge when it's finished, one has a minus charge when it's finished. In a covalent bond, the electrons are just going to be shared back and forth between the two atoms. There is one other type of bond we're going to learn about called metallic. A metallic bond is a little weird because the electrons come off of the atoms and start flowing around freely. They kind of don't belong to any one nucleus anymore. They start to kind of flow throughout the whole material. So we call that free-flowing electrons. So the types of bonds, when we have an ionic bond, it's going to be a bond between a cation and an anion. Usually that means it's a metal and a nonmetal. Not always, but usually. You need a plus charge, you need a minus charge. Most metals, right, they make a plus. Most nonmetals make a minus, so that's usually how it will work. That means you have to remember which elements are metals and which ones are nonmetals. You have to remember which things make a plus and which things make a minus. A covalent bond is going to end up being a nonmetal and a nonmetal bonded together. A metallic bond is a metal and a metal. That one should hopefully be pretty obvious. It could be the same types of metals down here. It could just be a copper and copper, or you could start mixing them together. You could have copper and zinc mixed together. Let's look a little bit more closely at ionic bonds when we transfer them. You transfer the electrons, it turns them into ions, and then the ions are attracted to each other. The joke is, I don't know if you guys have ever seen a James Bond movie, but there's always a joke that says that, he says, the name is Bond, James Bond. He likes his martinis shaken, not stirred. So the joke is, the name is Bond, ionic bond, taken, not shared. Okay. This is another little silly joke. The idea is that the negative charged ions and the positive charged ions are being drawn together. So let's walk through an example of sodium and chlorine. I'm going to kind of do this in two columns. We're going to have information about sodium in one column, and we're going to have information about chlorine in the other column. Sodium has 11 electrons. There is its configuration. You can see from its configuration that it has one valence electron right there. It's going to lose that valence electron to make an ion. So when it does that, you end up looking down here, your new outside energy level is level 2 now. You got rid of this one, so now you're down to level 2, and it has 8 valence electrons, which is full. So by getting rid of this electron, it dropped down to a full shell, and now sodium feels much more stabilized. Chlorine starts with 17. Here is its configuration. It has 7 valence electrons. You can see them right there. Now this time, it's only missing 1, right? So it needs to gain an electron. And now if you look, it has a nice full shell. In this process, we've made a cation over here, and we have an anion over here. We have a positively charged particle and a negatively charged particle. And if you remember, opposites attract, don't they? So this positively charged ion and this negatively charged ion are going to be what we call electrostatically attracted. They're drawn towards each other. And that attraction holds them next to each other, and that's what we call the bond. A bond is not a tangible object. There's no rope tying these things together. You can't reach out and touch it. It's just a description of the fact that these atoms are now staying near each other. Another way to think about this is to look at metals and nonmetals and their characteristics in terms of their ionization energy and their electronegativity. So a metal wants to get rid of an electron. A nonmetal wants to gain an electron. The reason that works out well is because the metal has a low ionization energy and the nonmetal has a high electronegativity. So the metal is easily able to get rid of an electron. You can take one away easily. The nonmetal is trying really hard to attract the electron. And so that's a perfect pair. That's why we can get that electron to transfer from the metal to the nonmetal, making a cation and an anion, and then that positive negative charge. And that's why they're connected with, their electrostatic bond, right? So you can see our electron configurations are coming back. Our classes of metals, right? Classes of elements, metals, nonmetals, metalloids. Our periodic trends are coming in. Our cations versus anions, how many protons, how many electrons. All of these things start coming together and are the reason why certain bonds form. And that's going to be really important because then we can start taking these molecules, putting them together to make new molecules during a reaction, right? And it's all starting with the things you've learned earlier this semester. We've been learning a lot about individual atoms on the periodic table. Now we start putting them together in combinations to make these bonds. One thing that's interesting about ionic bonds is that you end up kind of stacking them together in 3 dimensions to make crystals. So ionic compounds really like making crystals because you can have positive and negative attractions in all 3 dimensions and they alternate with each other. We're going to go over a couple of the properties of ionic compounds. They're typically solids with really high melting points. They're pretty strong bonds. You got to heat those up really hot before they start to melt. One interesting thing though is that they break very easily when you put them in water. The water molecule gets in between the atoms and breaks that electrostatic attraction. And so while it's very hard to melt them like, on the stove or something, you can easily dissolve them. If you heated up an ionic compound hot enough until it became a liquid, we call that molten, like molten lava. When you have something really, really hot that's like in a liquid form, it can conduct electricity because the ions are able to let that charge of the electricity kind of flow through it. Same thing when you dissolve them in water. When you dissolve it in water, we call it aqueous. Okay? If you have salt in water, the ions are apart and now the electricity can flow through that material. One thing that's really interesting to know is that the properties of the compounds are going to be very, very different than the individual elements. They're going to start with as atoms with certain properties, and then they're going to change into a compound that is very different. So for example, sodium is an explosive metal. You put it in water and it explodes. Chlorine is a poisonous gas. It's a chemical weapon, right? Used in war. Very, very deadly. It gets in your lungs and it makes your lungs fill up with fluid and you drown while standing there, right? So you put those 2 things together though, and you get sodium chloride, which is something you eat every single day. If you don't have enough salt in your diet, you actually die because your cells can't regulate properly, right? So you get two deadly, dangerous things. You change their electron configurations into something different, and now you have a completely new molecule with completely different properties because the properties are based on the electrons. If you change the electrons, you change the properties. And those electrons change during the bonding process, right? So I think that's such a great example to see how truly different those properties can be. All right, let's switch gears a little bit. We're going to do covalent bonds next. Covalent bonds are where electrons are being shared. It's not as good as ionic, right? It's not a perfect swap, but it's better than nothing. So if something can't make an ionic bond, the next best thing is to do a covalent bond. We end up typically with nonmetals and nonmetals. The atoms are going to share their electrons, which tricks the elements into thinking they each have 8. There are not enough electrons to go around to have a full shell for everything. But because they're sharing the electrons, they each feel like they have a full shell. So I'm going to use little circles like this to represent that. You have each atom donating an electron. You can see them color-coded. The green one has an electron to share, the blue one has an electron to share. When they're being shared, they each feel like they have 2 electrons here, right? So that would be the bond, the sharing of these. Because each atom is trying to have these electrons, they get physically close to each other, right? And that's what's keeping those atoms next to each other. You don't need to draw these pictures. I'm just going to show you a series of examples. You can see here we have 2 hydrogen atoms. They each have a valence electron to contribute, and then they share them. Now they feel like they have 2, which is better than they started. Here we have 2 fluorine atoms. They each have 7 valence electrons. They end up sharing these 2, and now they each feel like they have 8 valence electrons. They feel more stable that way. You can start getting really interesting, complicated combinations when they're willing to share. You could have 2 oxygens being shared to 1 carbon. Instead of each sharing 1, right, or each donating 1, sometimes you can donate multiple, right? You can start getting different types of bonds, right? We have, before it was a single bond, now look, this is a double bond. Instead of sharing 2 electrons over here, they're sharing 4 electrons. Things can start getting really big. You can get bigger and bigger molecules, more and more complex. The nice thing about covalent bonds is it opens up a whole realm of possibilities. Because they're willing to share, they don't have to be as particular with which atoms they bond with. So you get a lot more variety happening. The properties of the covalent bonds are kind of the opposite of ionic. They don't conduct electricity. They have low melting points. And they usually don't dissolve in water. They're not what we call soluble. The last one is metallic bonds. We don't learn very much about this. Really, we just learn that the electrons start to kind of flow around and they don't really belong to one atom anymore. We say that they are a sea of electrons. So if you can imagine, if you think of the ocean, the sea, the water just kind of flows all over the place, right? The reason metals can conduct electricity is because their electrons are not stuck onto the atoms like normal. So because their electrons can move freely, if you apply a charge to each side of a piece of metal, if you put a plus on one side and a minus on the other, right, you hook it up and you can drive the electrons in one direction. You can make them all flow in the same direction. So you turn your ocean, your sea, into a river. And that's what gets the electricity to flow through the wires and into your light, right? Things like that. So let's switch to watching this little animation real quick. So they're going to show you that, like, we don't care about the inside. We're only looking at the valence shell. So that's what those orange circles are about. In this metallic bond, you can see that the electrons just kind of detach and flow all over the place. They're not stuck on any one particular atom anymore. So all those valence electrons end up just floating all over. So the properties of metals is that they're typically a solid, except for mercury. They conduct electricity. We say they're malleable and ductile, and they have a big range of melting points. So we've kind of learned all of that already when we were learning about our classes of elements, remember? So hopefully that part is just a little bit of a review. So I know that's a lot of information to go over, trying to get through all 3 types of bonds. The types of questions I might ask you about this would be, what are the 3 types, right? I may give you a molecule and ask you to identify what type of bond it has. You would do that by trying to look at, is it a metal and a nonmetal? Is it a nonmetal and a nonmetal? Is it a metal and metal? I may ask you to explain why types of bonds form. I may ask you to explain the fact that, this is all based on valence electrons. Eventually, we're going to start learning how to draw these bonds, and that will be a whole nother part of the chapter is, how do I draw an ionic bond? How do I draw a covalent bond? Okay. All right. I hope that was helpful, everybody. Bye.